All right, today we're diving into a wild story. It's about how some of the most advanced tech we have, stuff we use every day, actually grew out of one of the most useless materials ever discovered. It's this incredible tale of physics, memory, and a single brilliant idea that, honestly, changed everything. So, here's the big question, the central mystery we're unpacking. How on earth did a weird metallic alloy, something with literally no practical use, become the blueprint for the AI that powers, well, everything? It sounds completely backward, right? But the answer, you'll see, is buried in the strange world of physics. So our story doesn't kick off in some slick computer lab. Nope. It starts in a condensed matter physics department with a material that totally baffled scientists and one researcher who saw a connection nobody else could. Okay, let's meet the main character of this first act, this spin glass. Now, despite the name, it's not actually glass. It's usually a metal alloy. And back in the mid-20th century, physicists were just fascinated by its bizarre magnetic properties. But for all its scientific curiosity, it had zero applications. None. It was, for all intents and purposes, completely useless. And believe it or not, that's the key to this whole story. Then came 1982. And this is the moment everything changes. A physicist, John Hopfield, drops this groundbreaking paper. He takes the weird, abstract physics that was developed just to explain these useless spin glasses and uses it to build a network that could actually learn and remember. And with that one move, he brought physics crashing into the study of the mind and basically rescued the whole idea of neural networks from the scrap heap of AI research. So what was Hopfield trying to do? Well, he wasn't just solving some small academic puzzle. He was going after one of the absolute biggest questions in all of science. You see, Hopfield wasn't interested in just any old problem. As he put it, he was hunting for a problem with a capital P. He wanted to understand how the physical gray matter of the brain gives rise to the mind itself. And to even begin to tackle that, he decided to start with a key piece of the puzzle, associative memory. Think about the difference here. A computer's memory? It's like a giant file cabinet. You need the exact file number, the precise address to get the info. If you're off by even one digit, you get the wrong thing or, just an error. But our memory is so different. The smell of lilacs can suddenly transport you back to your grandpa's garden in vivid detail. A tiny fragment triggers the entire picture. That right there is associative memory, and that's the magic Hopfield wanted to build. So to solve this biological problem, this mystery of the mind, Hopfield turns to a purely physical concept, a model originally designed to understand how magnets work. The tool he grabbed was called the Ising model. And you can just imagine it like this, a grid of tiny little arrows, or spins, that can only point up or down. The rule is super simple. The whole system always wants to find its lowest possible energy state. So when arrows next to each other point in the same direction, the energy is low. When they're all jumbled and misaligned, the energy is high. It's really just like a ball that always wants to roll to the bottom of a hill. Now, for a regular magnet, there are really only two downhill spots. All spins up or all spins down. Pretty simple. But in 1975, a couple of physicists adapted this model for the weirdness of those spin glasses. They let every single spin interact with every other spin, all with random strengths. And the result wasn't a simple hill anymore. Oh no. It was this vast, rugged mountain range, what they call an energy landscape, full of countless different valleys, each one a stable, low-energy state. This is where randomness gets kind of frozen into place. So, we have this rugged landscape, right? Full of countless little valleys. And this was Hopfield's big aha moment. He realized this physical model of a weird magnet could actually be a model for memory itself. The analogy he drew was frankly brilliant. First, he said a neuron can be on or off, just like a spin is up or down. Okay, makes sense. Second, the connections between all our neurons are like the random interactions between all those spins. And third, and this is the absolute key, a stable, stored memory is simply one of those low-energy valleys in the energy landscape. He had found a physical home for a memory. So just imagine this. To store a memory, you basically sculpt that energy landscape so your memory sits at the bottom of a valley. Then, to recall it, you don't need some perfect address. You just give the network a piece of the puzzle, a fragment of the memory. This places the network state somewhere on the side of that valley's hill, and from there, it just does what physics does best. It naturally rolls downhill, settles into the bottom of the correct valley, and by doing so, reconstructs the complete memory. It's so elegant. And this amazing breakthrough wasn't just some clever model. It lit the fuse that would eventually lead to the deep learning revolution, decades later. I mean, you can trace a direct line from that moment to right now. It all starts with the physics of spin glasses in '75. That leads directly to Hopfield's memory network in '82. Then, just a few years later, AI pioneer Geoffrey Hinton uses that exact same idea to build something called the Boltzmann machine, which was a very early generative AI. All of this work laid the deep conceptual foundation for the deep learning explosion that kicked off around 2012. And now, amazingly, we're finding that the transformer models that power things like ChatGPT are conceptually part of the very same Hopfield network family. It's all connected. And just when you thought this was all just cool history, Hopfield networks are making a huge comeback. It turns out that the attention mechanism, which is the absolute heart of modern transformers, is actually a new, more powerful kind of Hopfield network. And this isn't just a fun little did-you-know fact. It's allowing scientists to design AI more intentionally. It even helps us understand how things like image generators work. They're basically starting with a canvas of pure noise and then rolling downhill into a stable, coherent image, just like Hopfield's network settling into a stable memory. You know, this all ties back to a really profound idea in physics, captured in this famous quote from Philip Anderson: "More is different." And the idea is that when you scale up a system, when you have enough simple parts interacting, you don't just get more of the same. Totally new, surprising behaviors can just emerge from the collective. That's true for a spin glass, and as we are really learning now, it is profoundly true for AI. The intelligence isn't in any single digital neuron. It emerges from the whole. So we end on this thought. This whole journey started with physicists trying to understand a completely useless piece of metal. That weird quest gave us the tools to build machines that can remember, create, and learn. So the question we're left with now is, as these machines become more and more powerful and complex, could the very same physics that helped us build them be the key to finally understanding the artificial minds we've brought into the world?